In a groundbreaking astronomical finding, researchers have discovered ghostly neutrino particles coming from the galactic core. Due to their weak interactions with matter, neutrinos, among the smallest fundamental particles in the standard model of physics, have long proved elusive. The discovery of these elusive matter particles has allowed astronomers to map out our galaxy for the first time without using conventional light observations. This new row showing the Milky Way in neutrino light has added a hitherto unseen depth to our cosmic vision as we increase our grasp of the Milky Way's picture in everything from gamma rays to radio frequencies. How then did scientists discover that these particles are indeed emanating from the galactic center? Why are neutrinos known as the nature's ghost particles? What importance, if any, does the finding of neutrinos from the galactic center have for astronomers? Is the final and most crucial question. One class of particles, the neutrinos, sometimes known as the ghost particles, stands out in the enormous cosmic ballet of particles. These fundamental particles are considered members of the lepton class since they are indivisible and have a half-integral spin. There are three different forms of neutrinos, muon, tau, and electron neutrinos. The electron, muon, and tau are connected to their respective fundamental particles, respectively. Despite not being the building blocks of other matter, neutrinos are incredibly important in the grand scheme of things. Neutrinos stand out from other elementary particles due to their remarkable characteristics. First of all, because they are electrically neutral, not even the strongest magnets can detect them. They are also difficult to deal with because of their nearly non-existent bulk. They glide through planets, stars, and even human bodies at nearly the speed of light, with about 100 billion neutrinos passing through each square centimeter of our body each second. This means that trillions of neutrinos are passing past us undetected every second. They have the suitable moniker, ghost particles, as a result of their unsettling capacity. Neutrinos are extremely quiet particles, but they are crucial to our understanding of the intricate workings of the cosmos. You may be wondering, where did these particles come from? In both natural and artificial environments, numerous nuclear reactions produce neutrinos. High-energy reactions involving protons and atomic nuclei are among the most frequent events producing neutrinos. Nuclear reactors, nuclear bombs, and particle accelerators can all be used to artificially trigger these processes. On the astrophysical front, neutrinos can spontaneously produce themselves from nuclear events occurring in star cores. It's interesting to note that most neutrinos found on Earth come from nuclear processes occurring in the Sun, with a flux of about 65 billion solar neutrinos per second per square centimeter at the planet's surface. A supernova event is another source of neutrinos in addition to these. The key finding of a new study, however, concerns the process through which neutrinos arise in connection with cosmic rays. The high-energy particles known as cosmic rays interact with atoms to produce neutrinos. They come from a variety of sources in space. For a long time, scientists thought that high-energy neutrinos came only from galaxies outside the Milky Way. But astronomers have long believed that the Milky Way, our own galaxy, might be a source of these neutrinos. Cosmic rays colliding with interstellar dust and gas is a fascinating phenomenon that can produce both gamma rays and high-energy neutrinos within our galaxy. Let's examine this fascinating phenomenon's development in more detail. Cosmic rays can produce the unstable pion particle when they come into contact with the interstellar medium. Pions come in three flavors: positive, negative, and neutral. Pions are made up of a quark and an antiquark. The lives of the charged pions are only about 26.033 nanoseconds, after which they disintegrate. The neutral pion, on the other hand, has an even shorter lifetime of roughly 85 attoseconds. Gamma rays are produced during the decay of neutral pions, whereas extremely energetic electron neutrinos are created with the decay of charged pions. The discovery of gamma rays coming from the Milky Way's plane in earlier studies has led researchers to predict the presence of high-energy neutrinos in that region as well. Neutrinos, as was previously said, interact with matter very weakly, which makes it extremely difficult to detect them. Even still, finding and studying these elusive ghost particles is not an insurmountable challenge for scientists, and the manner it has been done on the South Pole of Earth will astound you. It takes a lot of patience and meticulous precision to detect high-energy neutrinos on Earth. Facilities like IceCube are essential to this attempt. Over 5,000 optical sensors hung along 86 threads make up IceCube, a mammoth detector that is housed at the Amundsen Scott South Pole Station in Antarctica. Through holes that have been drilled up to an astonishing 1.56 miles or 2.5 kilometers, these strings reach far into the Antarctic ice. Neutrinos generally travel through the Earth's atmosphere unaffected, although on occasion they come into contact with water molecules. Muons are produced as a result of these interactions, and they appear as light flashes inside the detector's sensors. Researchers can reconstruct the energy and, in some cases, even identify the source of the observed neutrinos by examining the patterns of these light flashes. However, the clarity with which a neutrino's initial orientation is recorded in the detector is crucial to correctly pinpointing its source. While some neutrinos have well-defined routes, others can produce complex light cascades that hide their sources, forming fuzz balls. As a result, verifying a detection and figuring out where it came from can need a lot of observations. Researchers used machine learning to examine more than 60,000 observed neutrino cascades gathered over a 10-year period in this groundbreaking work. This picture from the research paper shows how they were able to create an intriguing map showing the sources of neutrinos dispersed around our galaxy by feeding this enormous dataset into their algorithm. The galactic center is shown by a dot, and the galactic plane is depicted in this map as a gray curve. The areas with the greatest emission surplus are indicated on the map by the darkest spots. A startling finding is made when this neutrino map is contrasted with maps made using optical and gamma-ray frequencies. The majority of the neutrinos come from areas where significant gamma-ray counts have been observed in the past. The scientists painstakingly removed background neutrinos, particularly muon neutrinos, which are produced by interactions in the Earth's atmosphere and can considerably obstruct the detection of astrophysical neutrinos, in order to produce this neutrino map. A key component of neutrino astronomy, the straightforward reconstruction of particle direction, was made possible by the characteristic straight tracks produced by muon neutrinos. Due to the team's creative use of machine learning techniques, they were able to include 20 times as many events in their dataset, improving the directional information and ultimately producing results that were more exact and accurate than those of earlier studies. Analyzing the data, we find that the neutrino flux at the galactic center exceeds the background noise by about 4.5 times, a substantial 4. The abundance of detected neutrinos from the galactic plane offers strong evidence that the Milky Way acts as a source of high-energy neutrinos, even if it falls just short of the traditional 5 sigma threshold for high confidence. Given that photons have historically been the primary means of observation in the study of celestial phenomena, this finding represents a significant advancement. We now stand on the verge of an exciting possibility, learning new things about the cosmos by using particles that were once hardly detectable to map our world using neutrinos. It increases our capacity to delve deeper into the mysteries of the cosmos, and opens up intriguing possibilities to see reality in a completely new way. James Webb data were recently used in a study that suggested the universe may contain 26 quarks, 7 billion years old, or about twice as ancient as currently believed. Make sure you watch this episode if you missed it to learn more about this fascinating finding.